Hello, today we're going to do a load of experiments with H2O or water. We've all got it at home in the taps, and these experiments should use stuff that you have knocking around your house. They're simple, easy and cheap to do. The first thing you may notice as you're looking at my glass of water is that you can see my hand and my arm pointing in the wrong direction. Now that is all to do with the fact that water has a different density to air. So when light travels to our eye, it is refracted, which means it's bent. And so the light travelling to our eye from something like this picture is bent as it travels through the medium of water. It's like magic. So the arrow will point in the opposite direction. See? Now it's pointing left. Is that left or right? I don't know my left and right. And now it's pointing right. Is that right? Yeah. Now it's pointing right and now it's pointing left. I might have it the wrong way round, depending on whether I'm talking about my right or your right or left. Anyway, this is experiment number 1, displaying refraction. All waves, including light waves, diffract, which means they bend around corners, refract, which is when they change direction, travelling in a different medium, and reflect, like for instance, when you look in a mirror or on a shiny surface and you see light reflected. So you can play around, and if you notice, we can even see another cookie up there. And with different shapes of glasses and different movement of images through water, you can have a good look at how the movement of light changes. Ooh, ooh, it's a bit like a hall of mirrors. This way. If you thought that first trick was pretty cool, wait for this one. That one seems like magic. This one seems like super crazy. What you need to do is get a bag. Oh no, has mine got a leak? I hope not. And fill it with water. There's no goldfish in there, but just pure water. And I'm glad there isn't a goldfish in there because I am going to stick a skewer through this bag of water. Now I'm a bit worried that it might make a mess. So I advise at home you do this over a sink. I'm going to do it over a bowl, just in case. And I'm going to stick the skewer through the bag. Wow! Do you see that? No water is spilling out. No drips in my bowl. So now I'm getting a bit confident with this. I reckon the next stage is to try it without the bowl. I'm going to go for a second skewer. This is where it all goes wrong and I flood the room. Let's give it a go. And I can hear a small child crying in the background, so I might have to, after this one, yay, show my magic trick to my small child downstairs, but I'll be back to show you more. Okay, coming! Take the skewer, put this skewer through, but you have to just put it right through. Okay, I'm doing it without a bowl underneath, so go for it. Be confident. So push. Well done. Well done. Well done. Yay, you did it. Nice one. Okay.
Another one.
You want to do another one?
Yeah.
Okay. Hopefully we're not tempting fate, but we're going to go for 4 more skewers. Okay, and I don't want anything to get soaking wet. Go for it, Hux. Go for it. Okay, go. Push through. Whoa. Whoa. You have to do it straight through. Well done. Oh no. Oh no. No, it's that. It's there. It's done it. No. Okay. Never mind. Quick, quick, quick. Quick. More. Quick. Put the others in before we flood the house. Quick. Go on. Put one in.
Put it in the
No.
sink.
Do you not trust it?
Put it by the
Okay. It's going too wild. One more. Okay. And another. And another. Okay, we did it! Yay!
Mommy,
So I've dried everything off now. The reason that experiment works is not due to the water, although because water's transparent and you can see through it, it works really well to use water. But other liquids would do the job as well, because the secret is in the bag. The plastic bag is a polymer. Plastics are often polymers. They're made up of long chains, hence poly, and they're often called things like polythene or polyvinyl chloride. Anyway, the polymer chains, get this, they actually reseal around the skewer when you put it through the bag. So the skewer actually slides between the polymer chains, as it were. And that's why no water comes out of the bag. It's very clever. And water is perfect because you can see through it. So this next experiment is dead easy, and it only requires a piece of cardboard like this one here and a glass of water full to the brim. So I'm going to slide it in. It's very full. Some of it's trickling out. Okay, it needs to be really full, so I'm going to just top it up. There we go. And now I'm going to put the cardboard on the glass, like so, and then when I turn it round and let go, it's not full enough. Okay, gonna try again because that wasn't full enough. It will work, but I would recommend you do it over a sink, just in case. Okay, so here we go. When I turn it over and let go, cardboard sticks, and that is because the weight of the water is less than the air pressure pushing up on the cardboard. So the air pressure is pushing up, the weight of the water is pushing down, but because the air pressure pushing up is more than the weight of the water, the air pressure wins and the water doesn't get to come out. Clever, huh? Oh, I'm getting a bit thirsty now. That's another good perk of doing experiments with water. Yeah, it's nice. Our next experiment looks at something called the ideal gas law, which says that the pressure and the volume of an ideal gas is equal to a constant times the temperature. Gases have lots of particles inside, and they all are sort of moving around haphazardly. If you increase the volume, the particles are further apart. If you decrease the volume, they're closer together, which means they're exerting more pressure and the temperature goes up. So the volume and the pressure and the temperature all adjust accordingly, so that this is always a constant for every ideal gas. So what we're going to do in this next experiment is we're going to take a tea light candle and we're going to put it inside a dish of water, and as the candle burns, the gas will be used up here because it will take oxygen, which means the volume will go down, and so water will rise up hopefully through the glass to fill the space. So let's see what happens. Hopefully I can find something to colour the water with, because I tried this before and with just normal water I couldn't find any ink, so fingers crossed, because if it's with coloured water it shows up a lot better. Hey, I just realised that my children have watercolour paint, so I've now made the liquid purple. It might be a bit clearer to see the water rising up the glass. Here we go. Let's look at the ideal gas law in action. So, there we go, light my candle. So look, there's lots of gas in here currently. Lots and lots of gas. Now, the flame is slowly using up the oxygen because fire needs oxygen to burn. And there we go. Some of the liquid has travelled up the glass. You can see the purple liquid. And so now our tea light is floating. Let's give you a better closer up look. Is that working? Yeah, you can see the level of the purple liquid has travelled up the glass. And if we recap our ideal gas law, if you remember, as the volume of gas goes down here, which means the pressure of the air here is pushing the water up and in the glass. So our tea light travels upwards. Okay, let's sink it back down. There we go. Nice one. Our next experiment works because water has polarity. So if you look at a water molecule, it's made up of 2 hydrogen atoms and an oxygen atom, hence the name H2O. Now, it's called a polar substance because there's ever so slight positive charge to these hydrogens because they lend their electrons to the oxygen to form a bond, and they make the H2O molecule. So when water is mixed with other polar substances, the hydrogens turn into hydrogen ions in solution, which means that they're sort of H pluses because they've lost an electron, essentially. They're ions, they have a positive charge. And basically, if you mix water with substances that don't have polarity, water is immiscible, which means it won't mix properly. And we can see that when we mix water with oil. So for our next experiment, you need to get a bottle, like I've got here, and then we're going to pour some water into it. Okay, I should have just pre-put the water in so that I don't make too much mess. There we go. It might be nice to add a bit of colour to it. I'm going to see if I can get the old poster paints out again. Not poster paints, these are watercolour paints. And I'm going to add a bit of purple in. Come on, purple, paint out you come. Ew. Let's put it in there. And then make that a bit purple. Okay, I'm just mixing up a bit of purple water in here, so that I can make my water purple, because this will work better if you can actually see that the oil isn't mixing with the water. So I'm going to just pour that in now. Okay, that's kind of slightly purpley. Is that slightly purpley? Kind of slightly purpley. Let's pour that out and put some more of the purple concentrate in. Here we go. I'm just doing this all on the fly. There we are. Now, to show that water is immiscible with oil, I'm now going to pour some bright yellow oil, my purple. Here we go. And you'll see that it doesn't mix in, does it? It should just rest on the top without mixing. And if I give it a shake, instead of mixing together, it will be in little droplet bubbles all the way through. There we go. If you look closely, you can see that that is not all mixing into one. It's tiny little droplets of yellow, and then they rise to the top of the tiny little bubbles, and the yellow oil stays on the top and the purple water stays on the bottom. They don't want to mix, they don't want to get friendly, and that is all because water is polar. Try it and you'll see for yourself. It looks much better up close and personal. So remember those hydrogen bonds I was telling you about? They stick together quite well. They're quite good, strong, clingy bonds, which means that water can travel quite well along a string if you pour it on a string. So just gonna get another glass of water here and gonna wet my water to start it off. Then I'm going to put my string in here, and we're going to see if I can get this water to travel along the string into my glass. Here we go, good luck. Yay! See how it does that? So my empty glass is now filling up with water, and that is because of cohesion and adhesion. There we go. So this glass is now empty, and this glass now has liquid in. It's pretty good, huh? dead easy. All you need is a string and 2 glasses of water, or it's best done in a sink so that there's no spillages at all. And instead of pouring from the first glass of water, you could just use the tap to get the water to travel along the string into a second glass of water. Another really good water experiment you can do is if you get a balloon and you rub it on your hair, and then there will be negative charge on the balloon from static electricity. Then if you put a tap on, the positive charges from the water will get attracted to the negative charges of the balloon, and so you'll be able to bend the stream of water. That's a tap without the balloon, and that's a tap with the balloon held near. I wish that I could have showed you, but I didn't have a balloon. But hey, maybe I'll get one at some point and I can demonstrate to you. But it's a fun trick. If you've got a balloon and water, then give it a go. Now, during these times of coronavirus, we've all been washing our hands for 2 happy birthdays, and it's so important to wash your hands, not only because the coronavirus has an outer layer, essentially, an outer skin, which is broken down by soap, but because it takes that long, 2 happy birthdays, for it to be broken down. Now, this experiment shows really nicely how soap works so well. So here we go. I'm just putting a load of pepper into some water. So there we can see the pepper in the water. I'm now going to put my finger in the water and you'll see the pepper sticks to my finger. Got peppery fingers. Okay, but now see what happens after I've dipped my finger in some soap and I put it in the water. The pepper moves out. So to explain why that happens, pepper is actually hydrophobic, which means it doesn't like water. Once you put the detergent in the water, then the surface tension starts to go where the detergent is, and the surface tension is the sort of film that's almost on the top of the water. It's not exactly a film, but it's the tension that means like a pond skater can skate on top of water. And lots of cool things happen because water has surface tension. But the detergent stops that surface tension. So the water pulls back because it wants to retain the surface tension. And the pepper is no longer floating because the surface tension is gone. So it starts to sink. And as the water pulls back, it pulls the pepper with it, which is why you see the pepper moving out in that circular shape. So just to and let you know, soap is actually sodium stearate, and the soap molecule has a water-loving head, but it has a water-hating tail, hydrophilic head, hydrophobic. So when we wash our hands, for instance, the water-loving head loves being in the water, so we'll swim towards the water, but the water-hating tail likes all the grease and grime on our hands, so it will attach to that. And then as the water-loving head swims away, it will take the grease and the grime with it from the grease-loving tail, if that makes sense. So, for instance, when you wash your hands, you might often see scum form, because soap is sodium stearate, but scum is magnesium or calcium stearate, because the sodium stearate turns into sodium ions that go into the water, because it's got polar qualities, and then the calcium stearate is formed, which is scum. So that's why it's so important to wash our hands for 2 happy birthdays. Get rid of all the dirty stuff on our hands, including coronavirus. Another fun thing to do is to have a play with a bowl of water and different objects to see what sinks and what floats. For instance, this tub of air. Do you think it will sink or do you think it will float? Let's have a look. I'm going to put it right to the bottom. Woo! It's risen right to the top, and that's because air is less dense than water. The density of a substance is how tightly packed together its particles are, and something that's really dense, denser than water, will sink to the bottom. So for instance, glass is going to sink. There we go. It's really fun to have a play with what will sink and what will float. the density of water is about 1 gram per centimetre cubed, which means 1 centimetre cubed of water weighs about a gram. So anything that is heavier than 1 gram per centimetre cubed will sink in water, and anything that is less than that will float. So there you go. I really hope you enjoyed those experiments and that you'll try a few out at home yourselves. If you do though, please make sure you get permission and do it with whoever is looking after you, because these experiments can be quite dangerous unsupervised. So happy experimenting and see you next time. Bye.